Hi everyone. Today I'm going to talk about our work called VN Transformer. For perception tasks in autonomous driving, we want our models to not change their predictions when the input is rotated. This property is known as rotation invariance. For behavior prediction tasks, we want a similar property. If the input scene is rotated, we want the predictions to be identical, but rotated by the same amount as the input. This is known as rotation equivariance. Based on a paper from last year, whose idea is to replace scalar neurons with 3D vector neurons, we propose a rotation equivariant transformer architecture. We use the VN transformer to perform invariant classification and equivariant trajectory prediction. Some extensions I'd like to mention. First, we discuss different ways to incorporate non-spatial attributes. We explore an equivariant latent query mechanism, which speeds up inference and training. We introduce a notion of approximate equivariance and characterize how violations propagate through deep networks. Here's the link to our paper, and thanks for listening.
Hi, I'm Didash Chakraborty and I'm presenting Improving Motion Forecasting for Autonomous Driving with the Cycle Consistency Loss. We work in the field of motion forecasting. Basically, most motion forecasting models do forward prediction, which is given the history, they will predict the future. There is also backward prediction, which is given the future, can you predict the history? We observe that these are essentially the same problem because they obey the same constraints in a scene. Based on this observation, we formulate a cycle consistency loss. This loss is generic and can be applied on top of any motion forecasting model. Given the history, we predict the future using forward prediction. Then we do backward prediction with the same model where we use the predicted future to predict a history which we match with the ground truth history. We apply this loss on top of a motion forecasting model on the Argoverse test set, and we observe that applying this loss significantly improves our results. For a detailed analysis of our results, as well as a detailed explanation of how cycle consistency loss works, please visit our poster.
Hello everyone, welcome to our talk, Distortion-Aware Network Pruning and Feature Reuse for Real-Time Video Segmentation. The motivation of this work is that the previous frame and the current frame in videos share the temporal locality. We propose a novel framework to speed up any architecture with skip connections for real-time video segmentation pipeline. First, we transform the feature from the previous frame. Then, we perform partial computation of the backbone network, and this is done by dynamically dropping residual blocks based on interframe distortion. And our method generates two types of mask, a block pruning mask and a spatial mask. And our method provides a better trade-off between accuracy and the speed. And this is the qualitative results, and this is the visualization of the generated spatial mask. And thank you for listening.
Hello everybody, I'm Abbas Hamidi and our paper is about an intelligent modular real-time vision-based system for environment perception. So traffic violations, accidents and fatalities have significantly increased in recent years due to the increased number of vehicles on the road. In these circumstances, offering a practical solution to increase driving accuracy and road safety by designing and building an intelligent assistance system could be highly beneficial. So our sophisticated modular system consists of 4 components: lane detection, object detection, semantic segmentation, and distance measurement, which we will give in detailed information about them in our poster session. So just jump to the hardware section to show you how our system is implemented. Is here. So for implementing our module, a camera captures images from the vehicle's perspective, then a GPU performs neural computations, and finally a display indicates the system's result and any necessary alarms to the user. So here in real-world implementation, a laptop is used. So just to the jump to results section, we have developed an intelligent modular real-time vision-based system which is perfect integration of multiple improved networks along with the design GUI that you can see that provides any required warning to the user. Thank you very much.
Hello everyone, my name is Yunsheng Ma. Today I'm going to present our work on multitask vision transformer for semi-supervised driver distraction detection. Driver distraction detection is an important computer vision problem that can play a significant role in enhancing traffic safety and reducing traffic accidents. In this paper, we propose a multimodal vision transformer called VITDD to exploit inductive information contained in the training signals of both emotion recognition and distraction detection. In the real world, it's hard to get a large multitask driver dataset with all the required labels. So we train VITDD using the pseudo-labeled multitask learning algorithm, which uses the knowledge contained in an independent emotion recognition teacher model to train VITDD. Extensive experiments demonstrate that the proposed VITDD outperforms the best state-of-the-art approaches for driver distraction detection. Thanks for listening.
My name is Alexander Kim, and I'm introducing PolarMod. PolarMod views a 3D motif tracking task, where as input you get 3D motif detections, and as output produce temporally linked object instances as a tracking sequence on a temporal graph, where objects are nodes and edges are pairwise relationships. Unlike other methods, we focus on these pairwise relationships and allow the model to implicitly learn object information and track it over time through a contextually aware message passing algorithm. Our main contributions are threefold. We introduce a multiplex graph structure to represent the tracking sequence. We introduce localized polar edge features that are better at providing a motion prior to our model. And we introduce a technique for online graph construction to apply our method to online tracking scenarios. Through evaluation, we show state-of-the-art results on the NewSys dataset, as well as other benchmarks. With ablation studies, we show that each of our contributions is valuable, and we also show that our method indeed generalizes better between datasets and cities compared to other methods. Thank you, and check out our website for more information.
Hi, I'm Zoron. I will introduce our paper, A Graph Representation for Autonomous Driving. The efficient scene representation is the key to apply deep learning to behavior prediction or planning. We propose to encode the whole scene as a graph and process it with graph neural networks. Within the graph, node attributes consist of object properties and motion information in a global coordinate system, and edge attributes consist of pairwise relative motion information. Each agent pays direct attention to only the closest objects and aggregates information of a larger scope through edges. Because it works in a global coordinate system directly, it has identical complexity for single and multi-agent settings. And to reflect the scene dynamics, we also propose a space-time graph, which builds the graph not merely with the static status, but also the estimated future positions. Thank you.
Hi, Camel tries to learn the cost map parameters that yield optimal paths in the off-road environments. The cost map usually encapsulates the features obtained from the perception modules for the path planning. Off-road environments being rich in features with multiple classes and complex terrains, handcrafting these cost parameters would prove to be an inefficient strategy. Hence, learning these cost values would remove the laborious task and yield optimal path. Let's see how this is being done. So initially, we take our input, which is from the camera and the LiDAR point cloud. We then input it to the Camel architecture, which generates a cost map upon which a path planning algorithm is computed, which yields the throttle and the steering commands. These are some experiments at the simulation and from real world. Come check our poster at the ML4AD workshop at NeurOps 2022. Thank you.
Hi, I'm Peter from NVIDIA. DivStack is a new architecture for autonomous vehicles that is differentiable and modular at the same time. The key idea is to make the standard modular stack differentiable and train it jointly end-to-end. DivStack is like a neural network, but it has interpretable interfaces, intermediate losses, and it retains algorithmic components like a planner or controller, thus combining data-driven learning with interpretability, generalization, and safety guarantees. Our stack has a learned prediction model, a handcrafted planner, and an MPC controller. The standard stack trains predictions for prediction loss. DivStack trains for a combination of prediction and end-to-end losses by propagating through the control and planning algorithms. Our key result is that training predictions end-to-end substantially improves the final plan trajectories without sacrificing prediction accuracy. For example, by reducing small spurious prediction errors that would otherwise impact planning. Come to the virtual poster for more interesting results. Thanks.
Hi, I'm Anand Rory. The recent use of deep learning-based local descriptors has significantly improved the performance of algorithms for rigid point cloud registration. We test their abilities and limitations in the automotive LiDAR setting. For this, new and challenging benchmarks are needed, which we address with our general method for generating challenging registration sets. Using these sets, we produce a ranking of registration algorithms. We find that the best results in both accuracy and speed are achieved by advanced TransAC. We test the robustness of new registration algorithms to rotations, offsets, and low overlap. We also test the transferability of deep learned descriptors to previously unseen locales. Please visit our poster and paper for more details.
Hello, I'm Stefano, and I'll introduce the paper Safe Real-World Autonomous Driving by Learning to Predict and Plan with a Mix of Experts. Unimodal data-driven planners are known to suffer of mode averaging, and they could predict colliding trajectories. To improve the safety of these systems, we propose to model data uncertainty to find collision-free trajectories that can be safely executed on the self-driving vehicle. In this paper, we propose SafePathNet, a unified system for prediction and planning with the same machine learning model. This machine learning model is able to predict multimodal trajectories for both the self-driving vehicle and the road agents. Leveraging these distributions, we select the safest trajectory for execution on the self-driving vehicle. We tested our approach also on public road on a real self-driving vehicle. For more information, please come to our poster or look at our paper. Thank you.
Hi, I'm Lee, and I'll talk about the paper Finding Safe Zones of Markov Decision Processes Policies. This is a joint work with Ishai Manso and Michal Moshkovitz. The problem we consider is the following. Consider a Markov chain which is into this plane, policy on some NDP. The safe zone is a small set of states that contains most trajectories from the starting state to the final state. The goal is to minimize the sample complexity, that is the number of trajectories sampled, to find a safe enough safe zone. One possible motivation for safe zone is the distribution of roadside units for autonomous vehicle to infrastructure, and ideally a small safe zone would cover popular commute efficiently. That would give us safe autonomous transportation. So for the results, we show that finding a safe zone is in fact NP hard, even for small horizon of 2, and efficient approximation algorithm is provided in the paper. If you're interested, come check out our poster.
I am Isha speaking about our paper Improving Autonomous Driving Planning with Closed-Loop Weighted Empirical Risk Minimization. Typical imitation learning or behavior cloning techniques suffer from predictive bias towards open-loop behaviors. Upon deployment over time, small errors compound, causing poor inference time or closed-loop performance. We propose CWERM to address this, and it works as follows. In the identification phase, a traditional behavior cloning policy is trained well before convergence. Using a closed-loop evaluation simulator, difficult samples are constructed as the error set, and in the upsampling phase, a model is trained with this set upsampled. After the upsampling experiments, we see up to 35% improvement in collision avoidance metrics. Here are some examples of improvements by our candidate on the right, avoiding front and side collisions, showing subtle behavior changes. If you would like to learn more, please stop by our poster. Thank you.
Hello everyone, this is presenter Jung Min Kwon at Yeoman's University, and I'm going to talk about missing traffic data imputation using multi-trajectory parameter transfer, the LSTM. The considered virtual scenario in this paper is that the operation of an RC which collects the traffic data is temporarily failed. So our goal is to improve the imputation accuracy while reducing the training inputting time. Our proposed solution designs the lightweight architecture for a low complexity data imputation algorithm based on multi-trajectory parameter transfer, the LSTM, which is also called MPT-LSTM. The proposed algorithm consists of 3 main steps. First step is data separation, and the second step is extrapolation, and the final step is spatial interpolation. The experimental result shows that the proposed algorithm shows better performance compared to the other algorithms in terms of space and time complexity and imputation accuracy. So we can conclude that the proposed algorithm improves the imputation accuracy while reducing the training inputting time.
None of the previous self-training works focused on the data properties, so we just proposed a 2-stage pseudo-label generation algorithm to capture the uncertainty information during the pseudo-label generation process. Firstly, the basis initialization net is proposed to initialize the basis of EM algorithm. Then the EM algorithm is used to generate the uncertainty-aware pseudo-labels. Finally, they are used to retrain the model in an uncertainty-aware way. In the experiment, we show our advantages in image classification and image segmentation tasks. And the results just shows that our results are better in most of the criterions.
Training deep neural network from noisy label is an important and challenging task. Inspired by the physics, we propose a novel potential energy-based mixture model for noise label learning. The proposed method is realized by a distance-based classifier with the potential energy utilization on its class centers. By applying the method, the DNNs can learn better representations that preserve the structure from the date, resulting in a better noise tolerance.
I'm Junyoung Lee from Yonsei University. We focus on the ensure the safety of the autonomous driving policy. Many car manufacturers now manufacturing an autonomous driving system with the deep learning algorithm, but we does not know how it works, so we cannot ensure the safety. So we need to mathematically prove the algorithm or some boundaries that here is safe, but outside of here is unsafe. So we want to measure the difference between me and other cars policy, and through the safety reason. So we focus on the safety issue.
Hey, this is Plant. Plant is a planning transformer. Plant can not only drive in difficult urban environments, but also show on what vehicles its decisions are based on. Vehicles with a bright yellow box are less relevant, and red boxes are highly relevant for the current decision. Here we brake because of the cars in front of us. Interested in how we are doing this? First, we tokenize the current scene. Each object is one token. We use a standard transformer to process this information. We use a waypoint loss on the future position of the ego vehicle, and we supervise the future of the other vehicles. Since we use a transformer encoder, we can then visualize the attention weights. Want to know more about Plant? Come and visit us at our poster.
Hello everyone, my name is Loic, and today I'm going to talk about the multimodal GAN for 3D urban scenes, a Valeo AI project. In this paper, we address the problem of generating 2D RGB images with consistent 3D representations. Current methods combining GANs and neural rendering get good results on human and animal face datasets, but when we apply them on more complex datasets such as urban scenes, they fail to jointly generate the image and estimate the depths. Look at how the world is badly positioned. Corresponding depths are supposed to be near and wide. So our goal is to determine if we can extend existing methods to work with them. To fully exploit the urban scenes datasets, we decided to incorporate LiDAR information in the pipeline. By doing so, results look better. We are able to generate urban scenes while being able to freely move inside generated scenes, for example upward, laterally, and forward. More details about how we incorporate the LiDAR can be found in the paper. Thanks for your attention.
Hi, my name is Niklas, and in the poster session I'll be talking about King, a novel gradient-based generation procedure for safety-critical driving scenarios. King iteratively resimulates the scenario in closed loop and adjusts the trajectories of other agents via gradient descent to make the scenario more challenging for the agent under test, finally inducing a collision. In our experiments we show that fine-tuning an imitation learning agent on these scenarios leads to better collision avoidance.
Hello everyone, I'm glad to introduce our work enhancing system-level safety in autonomous driving via feedback learning. So the current autonomous driving system consists of two main components, perception and control component. Usually the perception component, which is a deep learning-based model, is trained isolated with the control component. This results two main issues. First, the error propagation to downstream control component. And secondly, the control component cannot evaluate the correctness of the perceived environment. To resolve the above issues, we propose the framework with this rulebook component. With this rulebook component, we can predefine some system-level safety that the system have to obey. And during the training phase, the rulebook will output the violations, which will be transferred into the rulebook loss to help the training of the perception model. And to check more details of our work, please go to our poster session. Thank you.
We present imitation learning combined with reinforcement learning using simple rewards can substantially improve the safety and reliability of autonomous driving policies, particularly in the most challenging scenarios. Our method is built on the intuition that imitation and RL offer complementary strengths, where imitation increases realism and eases to reward design burden, and RL improves safety and robustness, especially in the rare and challenging scenarios in the absence of abundant data. We propose a simple objective to combine the benefits of imitation and RL by optimizing the weighted sum of the RL returns with the imitative log likelihood. We build our method on the widely used software actor credit framework with an additional behavior cloning term added to the actor objective. We call our method BCSAC. We combine collision and offer reward additively as a simple reward function. We show that this simple approach achieves better performance overall, especially in the more challenging slices where the performance of the baseline methods, behavioral cloning, and model-based generative adversarial imitation learning substantially decrease. Thank you.
Today I'm going to present our paper with the virtual stereo-based augmentation for depth estimation in automated driving. Classic depth estimation techniques use LiDAR and stereo cameras in cars, but this is expensive to calibrate and suffers from sparse information and phantom points due to reflective surface. Recent work has been done in monocular depth, which is cheaper and easier to train, but less accurate. Our approach uses two nearby vehicles to form a virtual stereo pair. This adds an additional loss to regular monocular depth and extends the baseline for depth estimation. We use SIFT to match common key points between two images. This helps us select candidates for a virtual stereo pair. Remote relative pose is necessary for building loss between ego view and the remote view. In our work, the relative pose is estimated based on a neural network. Since there's no publicly available dataset for training, we use the Kala simulation engine to model the widely used KITTI dataset. The virtual stereo approach outperforms the monocular-only approach by about 8% and is better than the local stereo, which has stereo cameras mounted on the same car, while being more cost efficient.
Hi, I'm Pasquale Antonante, and I'm going to briefly introduce our work on monitoring of perception systems. This paper addresses the problem of safety from the perception standpoint. The reason why we care so much about perception is that perception failures, such as missing obstacles, can have catastrophic effects on safety. In this paper, we develop a monitoring framework to detect such failures at runtime. At the heart of the framework, we have the diagnostic graph. The diagnostic graph is a bipartite graph that efficiently organizes the different failure modes of the system, the relationship between them, and the available diagnostic information. We then propose algorithms that use the diagnostic graph to identify failure modes and introduce the concept of diagnosability as a measure of system robustness to failures. We tested our approach using Baidu Apollo and LGS-VL simulator over several realistic scenarios. We demonstrate that our framework has the potential of increasing the situational awareness, preventing accidents, and increase safety while incurring a negligible computational overhead. Thank you for your attention.
The motivation behind our work is twofold. First, lack of comprehensive datasets in the field, and second, majority of existing methods being fully supervised. Our contributions aim to address the above two issues. We introduce a novel and comprehensive dataset with diverse set of situations and annotations, including pedestrian attention in risky situations to enable research for risk perception in driving scenes. As can be gleaned from the table, our dataset is a first of its kind. We provide a weakly supervised framework which takes as input a sequence of frames and converts the different agents in the scene to nodes in a graph convolutional network. These nodes are then iteratively removed using partial convolutional network, and the risk object is identified based on the driver's response to the removed node. Our framework performs favorably against state-of-the-art methods on two driving scene datasets, the HDD dataset and our proposed ROI dataset. For more details, please visit our poster.
Trajectory prediction has been shown to be vulnerable to the throw attacks, where the attacker can drive along a throw-generated trajectory and fools the prediction of the autonomous vehicles and lead to collision. Therefore, it is essential for us to generating robust trajectory prediction models using adversarial training. However, we found conducting adversarial training on trajectory prediction is challenging due to three main reasons. First, the stochasticity of the trajectory prediction models obfuscates generating effective adversarial examples. Secondly, adversarial training on conditional generative models, which is usually used for building trajectory prediction models, is actually unstable. And lastly, but also importantly, the strict clean performance is required for the autonomous vehicles. For more details, please refer to our poster or our website. Thank you.
Hey, I'm Markus Känksepp, and I will give an overview of my paper, Calibrated Perception Uncertainty, across objects and regions in bird's eye view. To start with, there are two main approaches for perception, object-based and grid-based view. Both of these have limitations, so we should combine them. To support safe planning, we propose to output object-based uncertainty information, but additionally also information about particular rectangular regions in front of the car. For each region, we produce a probability that it includes an undetected pedestrian. This information is not included in FIRE semantic segmentation. As a result, we generated uncertainties for detected and undetected objects. With object-wise calibration, we were able to calibrate these. Come visit our poster.
Trajectory prediction aims for predicting future trajectories of road agents based on history trajectories. It is essential for autonomous vehicles to plan correct and safe driving behaviors. While many priors work focus on achieving higher prediction accuracy, few studied the adversarial robustness of their methods. In this work, we aim to consider an attacker driving along an adversarial history trajectory, which is similar to the wrong choice history trajectory from the dataset, but the trajectory prediction models will be fooled and predict incorrectly. As a result, the autonomous vehicle might collide to another road agent. In order to generate effective and realistic adversarial trajectories, we proposed adversarial dynamic optimization. To learn more about our methods, please refer to our poster or our website. Thank you.
Hello, I'm Zoe, and this is our work, One-Shot Learning of Visual Path Navigation for Autonomous Vehicles. The motivation comes from the demanding data requirements for deep neural networks and especially autonomous driving to deliver good performance. To address these challenges, we developed a novel end-to-end autonomous driving architecture with one-shot learning. We also build and test on a mini AV platform. The vehicle can learn to drive a previously unseen path autonomously after being shown the path once. We use a Siamese-style network architecture that manages the current driving task based on the memory of the one-shot drive. This is the camera view of the vehicle during a real-time one-shot test. And first sigmoid is the network output that manages the steering task. The current task is listed on the last row. Please visit our poster 54 to find out how one-shot learning can be used for autonomous driving applications. Thanks.
Hi. Real-world driving is full of output multimodalities when multiple actions or paths are possible. State-of-the-art architectures, however, don't often model multimodalities. Here we ask, is this important? My name is Mikita Balesny, and I did this work at the Autonomous Driving Lab at the University of Tartu, Estonia. Some state-of-the-art approaches do model multimodality, and some don't. So it is hard to tell if it is important because they all use different architectures and often different training data. Energy-based models have recently been shown to effectively model multimodalities and are easy to implement and train, so we use them as our case study. We take NVIDIA PilotNet as a popular architecture backbone, and we modify it to several model formulations, such as the standard regression, classification, Gaussian mixture, and energy-based. We wanted to see if multimodal models performed better than the standard policy shape. To learn how it all turned out, visit our poster today.
Object detection datasets contain a natural imbalance at the class level or at an attribute level. For instance, in the Berkeley Deep Drive dataset, motorcycle and bicycle classes have the least number of objects, thereby making them rare classes on which models perform poorly. Moreover, motorcycles and bicycle objects at night are even rarer, thereby making them rare slices on which models perform even worse. As a solution, we propose targeted active learning. In this figure, we illustrate one round of targeted active learning where motorcycles at night is a rare slice in the label data. Next, we mine images from the unlabeled set that are semantically similar to the regions of interest in the query set by using submodular mutual information functions. These images are then labeled and added to the labeled data to improve performance on the rare slice. We observe that the SMI functions significantly outperform other baselines by 5 to 14 points on realistic scenarios. To know more, please visit our poster on Talisman, which stands for Targeted Active Learning for Object Detection with rare classes and slices using submodular mutual information.